to the Physics and Astronomy public talk in this series. So I'm Greg Rudnick. I'm a professor of physics and astronomy at KU, and I'm going to introduce our speaker, who we're very happy to have, Dan McIntosh, Professor Dan McIntosh from University of Missouri, Kansas City. I've known Dan for a long time. We're actually academic brothers. We had the same PhD advisor at the same time at University of Arizona, and we kind of went all over the world and ended up 45 miles from each other. So it's really wonderful to have him here at the same time as I am, so on a scientific and personal level. So Dan got his PhD from University of Arizona after going to undergraduate at UCLA. He graduated from University of Arizona in 2001. Mm-hmm. Yeah, same year as me, so we were really parallel. And then he went to University of Massachusetts in Amherst, where he then did a postdoc, and then got an LTSA, which is a long-term science fellowship that NASA has. So he then stayed for a few more years at UMass as a NASA science fellow, and then got the faculty job at University of Missouri, Kansas City. And Dan's kind of a well-known expert on studying galaxy populations, galaxies and merging especially. So he's done a lot of work on studying how galaxies merge and their shapes are altered. He's working on one of the largest Hubble Space, I think it is actually the largest Hubble Space Telescope program in existence, called CANDLES, which you may or may not talk about a little bit. That's doing kind of wide and deep images with the Hubble Space Telescope and really unveiling a lot about the galaxy populations billions of years back in cosmic time. And so he has a really wonderful perspective on what Hubble has contributed to astronomy, and we're really happy to have him here. So without further ado, let's welcome Dan.
Thank you, Greg. Can you do the lights? I want to see if these lights actually... Nope, don't do that. Can somebody get those lights? So thanks a lot, Greg. That was great. Greg and I have known each other now for 21 years. That's pretty wild. All right, thank you, everybody. Thank you for coming out today. I want to kick this off, set the stage with just a little bit of history for a minute. So now, more than 25 years ago, oh, there we go. NASA launched arguably the most well-known scientific instrument in human history on the shuttle. And a day later, the fearless crew of the shuttle Discovery, including Professor Steve Hawley, right there on the right, from KU, put Hubble Space Telescope into orbit just a few hundred miles above the surface. Some people don't actually realize the Hubble Space Telescope is only about 350 miles above us. So that's about the distance from here to something like Oklahoma City. And after a couple months of checking things, I'm going to have to stand over here because it doesn't like me from that far away, and getting Hubble Space Telescope tuned up and ready to go, they fired up and, oh no, Houston, we have a problem. Hubble's eyes were distorted. The images coming from the Hubble Space Telescope were distorted, and it took a couple years to figure out what the problem is. And so here is what they had hoped they would see when they looked at a star, and they saw something more actually like this. This would be a ground-based picture, this would be a space-based Hubble picture, and they had these distorted images. And this funny-looking thing right here is the actual eyeglasses that they then, a couple years later, went back with the shuttle and installed on the first servicing mission to the Hubble Space Telescope to give it 20/20 vision. So here's a nice picture of a nearby galaxy on the left, and this is what Hubble looked like when its vision was corrected as we had hoped. And 4 servicing missions with the shuttle since, each time Hubble Space Telescope has been made into a better and better machine by putting on the latest technology of detectors and cameras and so forth. And as Greg was saying, I actually feel very fortunate to have been part of Hubble projects almost my entire career, for almost 20 years, and in particular 3 big teams I've been involved with, starting with a next servicing mission when they put on a brand new camera, better than the cameras before, called the Advanced Camera for Surveys. And here it is in the laboratory. It's basically just like a camera, a fancy camera that's inside your iPhone or your cell phone, a little bit bigger. And it goes in that big box, and the astronauts put it on a telescope, and now we have a much better, brand new, basically, Hubble Space Telescope imager. And so I was part of 2 teams that studied tens of thousands of distant galaxies with that great new instrument. Gems and stages, got to visit people all over the world, colleagues from different countries. We had team meetings in Germany sometimes, in Nottingham, and a really rewarding experience in my early career when I was a postdoc. And then the last servicing mission in 2009, astronauts put on the Wide Field Camera 3. This is even better than ever. So again, basically making a brand new telescope out of Hubble Space Telescope when it was already almost 20 years old at that time. And from there, right away, we got what was called a legacy program. So a group of us, actually quite a large group, it's about 100 astronomers, both in the US and internationally, wrote 2 competing proposals to ask for time with the Hubble Space Telescope, and basically had the same idea. And so the people at Space Telescope made a marriage between Harry Ferguson here and Sandy Faber, who's actually, when she was younger, one of the scientists who figured out what was wrong with the Hubble Space Telescope. I actually found out recently in a cool documentary. And so this is CANDLES, and it's the largest ever before, and there won't be another survey as big as far as studying the largest patch of the sky and the most distant galaxies. And I'm still working on it today. This is one of my students, PhD student Kameshwara. I'm way in the back somewhere. And this guy right there is actually the first student I worked with at UMass. He was a grad student just starting when I was a postdoc, and now he just became professor at Mizzou like 2 days ago. Yichen Guo. So that's cool for us galaxy people in the Midwest. All right, so over the last 27 years of Hubble Space Telescope history, as a scientist, as an educator, and as a citizen, I've reflected a lot on this great space observatory. And so tonight I'm going to share with you, first of all, what were the legacies, or what are the legacies of the Hubble Space Telescope? And later on we'll talk about why was the telescope named after this guy Edwin Hubble, who was Edwin Hubble, and how was astronomy in the United States different back in his time, which is now almost 100 years ago, than compared to today. And finally, I'm going to end the talk and get a little bit political, so hold on to your seats. And I'm going to answer the question, how much did Hubble cost? And the answer to the question of whether or not it's worth it has a lot to do with what's going to be the future of US astronomy and science, I think. So first of all, I think one of the greatest legacies of the Space Telescope are these images that capture everybody's imagination. Just like you, I see an incredibly beautiful image. But also as a teacher and a scientist, I see this fantastic picture. This is basically a snapshot of what's going to happen at the end of our sun's life, or so we think. Maybe there's theories that are changing a little bit about that. But basically we see the outer parts of the star being cast off. This thing's called a planetary nebula, but all that glowing yellow and orange is the outer layers of a star that died. And at the center is this little white dot. That's literally a diamond about the size of the Earth, called a white dwarf. It's the core that's left over, the corpse. When I teach my intro astronomy classes, I talk about stars have lives, they get born, they live their lives, they die, and they leave behind corpses. And that's the kind of corpse that the sun will leave behind. If you go on the internet, you can find dozens, hundreds even, of fantastic, beautiful images from the Hubble Space Telescope. And again, as an educator, I think about how all these images help engage citizens of all walks of life in our amazing and vast universe. So Hubble has shown us spectacularly clear pictures of things that are familiar to us, like Mars, and very exotic objects. Hubble Space Telescope has given us views of all the different life stages of stars, from star birth to infancy, all the way to the dying last days of old age stars, like this star right here, seen over a period of a couple years as its outer layer is expanding away. It's revealed mysteries about the deaths of stars. These are all versions of similar, well, this one, lower right, and upper left are also planetary nebulae, like the other one, which are sort of stars like the sun dying. The lower left is when a really massive, rare monster star blows up. It leaves a supernova remnant. All these are death throes of stars. It has given us really fantastic views and new information about star factories, places that stars are born at all different relative scales inside the Milky Way galaxy, like in these 3 pictures, and also in external galaxies, such as this galaxy right here. So the brownish region right here, for instance, is an area where star factories are, and new stars are being born or produced right now. It has given us the greatest looks of my favorite objects, these vast galaxies. You can think of a galaxy, every single galaxy is like an island of billions of stars held together by gravity. They're the birthplace of all stars. Stars are only born in galaxies. That means they're the birthplace of all planets. They are where the chemistry for life is produced through the formation of stars and the death of stars. And we see galaxies by themselves. We see them in pairs, sometimes interacting. As Greg was explaining up in the upper right, those two objects are two galaxies that are intertwined, gravitationally going to merge and make a larger galaxy in the future. We see them in groups, and we see them in these vast cities of galaxies. And finally, Hubble was able to reveal the presence of unseen dark matter. So each of these images, at the center of the funny one that looks like a smiley face on the left, is two big roundish galaxies we call ellipticals. The lower right is a single one of those objects. And in both cases you see these arcs, almost a complete circle in blue. The dark matter that holds those galaxies together, which is it spans a much larger region that you can see here on the picture. It bends light from the background behind these galaxies, behind the dark matter, just like the bottom of the wine glass. A glass lens bends the light of the little blue dots. And so if you're a little blue dot, like a background galaxy, you just look like a little round blob if there's no dark matter lens in front of you. But if a dark matter lens is in front of you, it turns that blob into an arc, or if you're perfectly lined up, into a circle. It's called an Einstein ring. And so that blue light in these pictures are very distant galaxies behind the big orange blobby galaxies. And like a lens, it distorts the background image, but it also magnifies the background image. So we can actually use this dark matter as a natural gravitational telescope to study the most distant galaxies in some cases. So scientifically, the Hubble Space Telescope has completely revolutionized how we think about astrophysics and astronomy. It's basically rewritten all the textbooks. And we can quantify this in a lot of different ways. We can get a little bit nerdy and talk about the number of papers, scientific papers that have been published because of the Hubble Space Telescope. Now it's over 14,000. That's quite a contribution. We can talk about the number of astronomers over the world. More than 15,000 astronomers from all over the world, individual people, have used the Hubble Space Telescope, produced science with it. And if you're really into computers and understand what a terabyte is, it's made a lot of data. So what makes the Hubble Space Telescope so special? It's not that it's a big telescope. It's actually a pretty run-of-the-mill telescope. So what I'm showing here is a little graphic of the size of the primary mirror. So astronomers call the main mirror that the light hits from out there sort of a bucket. It collects light. And the bigger the bucket, the more faint light you can see, the farther you can see. And so Hubble's mirror is a diameter a little bit more across than a person is tall, but that's basically the same size mirror that Hubble himself used 100 years ago on the Mount Wilson Observatory outside of Los Angeles, which I'll talk about in a minute. And so it's not the size of the mirror. I mean, compared to the largest telescope in the world, which is this one right here, so there's a mirror that size in this object and in this object. This is a big telescope called the Keck telescope in Hawaii. It's not the size of the mirror, it's because of where Hubble is. Placed above our atmosphere, it allows us to see these incredibly clear and detailed pictures. So really nice ground-based telescope picture of a star cluster, and Hubble can zoom in and resolve individual stars and even see these tiny, tiny little stars inside of that image. That allows us to see detail like we can never see on Earth. It also allows us to see very, very distant objects. At the time of Hubble, the furthest we could see, this is going nearby to basically the edge of the observable universe, we weren't even getting halfway there with the best telescopes on the ground. And now Hubble, with its souped up cameras, is getting out to 90–95% of the age of the universe in terms of looking back. And we'll talk about that in a minute also. All right, scientifically, forget the detailed number of papers and people using it. Probably what makes Hubble so important is that it's answered scientifically some of the biggest questions in science and astronomy. Questions revolved around humankind questions, like what is our place in the universe? Questions like how old is the universe? What is it made out of? How did we get here? What is the fate of the universe? And so what I'm going to do for a couple minutes now is I'm going to run through the 5 greatest scientific legacy achievements that Hubble has done that I think most astronomers, most scientists would agree on. And I'm going to start with my favorite, which is what some people call the greatest image ever taken by people. So this image is taken now 22 years ago, so not too long after Hubble's all fixed up. And to get an idea why this image that doesn't look much different than a background star image is so special, it's because it contained thousands of galaxies that we've never ever seen before in that one image. Basically every single speck of light, except for 1 or 2 or 3, is a galaxy at a different distance away from us in one part of the sky. And so it gave us a timeline, it gave us a little survey of galaxies, at least in that one direction. It was the deepest image ever taken. To get an idea for why this is so important, this gives us basically a way to measure the inventory of all the stuff that's in the universe. And to put this in perspective, imagine you picked a completely random part of the sky that was empty. Like you looked at it with your binoculars, you looked at it with the good telescopes. There's no stars in the way, there's no big nearby galaxies in the way. It's basically empty. And we decide we're going to spend about 10 or 11 days using the Hubble Space Telescope just staring at that empty spot. And to give you an idea in a human sense how big that spot is, imagine holding a penny at arm's length. The spot's about the size of Abe's eyeball on the penny. The penny at arm's length is about the size of the disk of the full moon. So we're talking about a spot on the sky much smaller than the full moon. I mean, kind of like this dot on the ceiling. Maybe that's even too big. And we took another image like the last one, but even deeper. So we call it the ultra deep field. The previous one was called the deep field. Astronomers are funny like that. This image contains 10,000 galaxies. So it was an empty patch of sky nearby, but looking really deep, really far out, far away, distant, it has 10,000 objects. There are only a handful of stars. Everything else is a galaxy. So stars have the little diffraction spikes, the little crosses. So that's a star, that's a star, that's a star, that's a star. I always feel like there's one other one in there somewhere. Maybe that's one. Everything else is a galaxy. And each galaxy contains billions of stars. And so just simply saying, well, that was a random patch of sky over there, then probably all, like a patch over there, on the other side of the Earth, a patch that way, they're probably all going to be about the same, about 10,000 galaxies. And so we can add up all those patches and multiply by the number of patches 10 times 10,000, and we have an inventory. We know, as a pretty good estimate, that the universe contains hundreds of billions of galaxies, each galaxy containing billions, even hundreds of billions of stars. And it's hard to actually wrap our mind around such a big number. One thing we do in intro astronomy is we say, well, if you consider every beach on Earth, all over the world, you know, beach is 100 yards across, I don't know, 10 feet deep, and every single piece of sand is a star, that's how many stars in the universe. I don't know if that works any better than this. The one I like is every single person on Earth, all more than 7 billion people on Earth, you each get 24 of your own galaxy, little islands of billions of stars to play with. That's another way to think about how big the cosmic inventory is, but it tells us what's in the universe. It gives us a really good understanding. Now, because galaxies contain so many stars, they're really bright. We can see them at very great distances. So the same image is also a time machine. So imagine this is the image right here, that little square. And we're looking at galaxies. Some are near, some are farther, some are really far. And because of this nice property of light that it has a speed. It takes time to go from here to there. So a galaxy 1 billion light years away, its light leaves that galaxy with information, a snapshot of what the galaxy looked like then, 1 billion years ago. And 1 billion years later, finally, the message comes to us. And we're like, aha, we know what the galaxy looks like at that time. So by comparing galaxies at different distances, we're comparing them at different cosmic times, from early on in the universe to the present day, about 14 billion years after the Big Bang. And so we can map the development of galaxies. We could do detective work and compare populations to figure out how the universe has changed. And it has changed a lot by looking at the universe like this. This is actually what I like to do. I call myself a galaxy demographer. I compare populations of galaxies at different times in the past. and then infer how the universe has changed. And so the candle survey, which is the largest ever done with Hubble, you can see compared to the ultra deep field, it's done much bigger surveys, almost as deep, and at 5 random pointings in different directions away from the Earth. Basically, what Sandy Faber likes to call the 5 most well-studied regions of extragalactic real estate. I love that. The reason she says that is that every major telescope, space-based and ground-based, has been pointed at these patches of sky, because we all want to, like, we're all kind of combining our efforts to actually get the most data for these patches of the sky, and Candles has the greatest Hubble Space Telescope images. So besides time machine and inventory, one of the key missions for Hubble is to figure out how old the universe is. And again, because it can see such exquisite detail, you take a really pretty picture of a ground-based picture of a pretty spiral galaxy like this, and look at what Hubble can see in all that detail in that one little section. And that allows, at least for nearby galaxies, Hubble to see individual bright stars. Like in this picture right here, this is a different galaxy. It's near to us. It's actually our sister galaxy, the Andromeda galaxy. And we have found, in this case, one single star that's been observed at different times. You can see it's getting brighter and brighter. And there's a certain special kind of pulsating stars that they get brighter, dimmer in a very regular time. And how long it goes from bright to dim back to bright again tells us exactly how bright it really is. So it's as if you see a bright light in the distance, but you have no idea how far away it is. But if you knew it was a 100-watt light bulb, then you take your digital camera and take a picture of it and measure how bright it appears. You can actually, with a very simple high school formula, figure out exactly how far away that is. So by able to map out how far away the stars in that galaxy is, it tells us how far away the galaxy is, and with some other math we can actually use that to figure out the expansion of the universe and the age of the universe, which I'll come back to in a little while. The fate of the universe. So we got the age. Also, again, because Hubble can see so far, it sees super distant, close to the edge of the observable universe galaxies. In each case, these blobs, the blue one at the center, the red one here, and this thing, these are very, very distant galaxies, baby galaxies from the early universe. And then a little while later, we just by chance catch a picture of them with Hubble, and we could see a new star. And this is one of those exploding stars where a monster star dies and briefly in that galaxy and briefly shines as bright as the entire galaxy that it belongs to. And those signposts so far away allow us a really accurate measurement of how the universe is expanding. It gives us a really good ruler from here to there, and so then we can figure out how the universe is expanding. And this experiment won 3 American physicists, astronomers, the Nobel Prize in Physics 6 years ago. Because by able to do this measurement, they were able to show that what we had naively thought as the universe was expanding, it must be slowing down. Just like you throw a ball up in the air, it slows down at some point, maybe even turns around and comes back. It turns out that as we're moving from the universe starts with the Big Bang to the present time, it's actually expanding faster and faster and faster. And we call this dark energy or runaway expansion. Hubble revealed really solid evidence that black holes exist. So again, always I'm going to keep on coming back to Hubble's ability to see detail is so important. So this is a big monster galaxy, a big round sphere of 1 trillion stars, and you can see this little jet of material coming out of the center. And with Hubble we can zoom in to the center and measure the motion of gas swirling around the center at very, very high speeds, very violent motion. And the only thing that explains such motion in such a small part of this galaxy is about 1 billion suns packed into a tiny, tiny dot, a supermassive black hole. And with the gas swirling around and feeding that black hole, causing that black hole to grow, it'll create these sort of jets that we see in this artist's conception, but we see in the real picture. And finally, early on, when we turned on Hubble, we started pointing at these star factories to get detailed pictures of what was going on. And looking at the center of each of these images is a baby, very, very infant, brand new star, surrounded by the gas cloud that it formed out of. And in almost every single case, we see these little disks of dust and pebbles and material, which are essentially the blueprints for the production of planet systems. So before Hubble, we had no idea that every single star makes planets. We know that there's planets around this star, the sun, but we didn't know about any other star systems really before Hubble. And this gave us the first clues that there could be something making planets. And now 20 years later, 25 years later, the Hubble Space Telescope has shown basically that all stars have planets. When you make stars, you make planets. It's just part of the recipe. All right, so that's the greatest 5 or 6 greatest scientific legacies that I think Hubble Space Telescope is responsible for. So why was this telescope named after Hubble? Who was he, and how was astronomy in the US done at his time? How is it different compared to now? So Hubble, shown here, was a great American astronomer. He was given credit for making 2 really key discoveries. That's the main reason we named the telescope after him, that really changed our understanding of the universe, fundamentally changed our understanding of the universe. Yeah, that's his cat. He's there with his cat Copernicus shortly before his death in probably in Pasadena, California. All right, so first discovery is he figured out the true nature of galaxies. If some of you like to go out in the summer and go stargazing and you're familiar with your constellations, the great square Pegasus is pretty obvious in the summer. You can see the Milky Way right there. You got to get away from the city. You got to be out where there's a clear sky and no moon. And if you know exactly where to look, you can see this little fuzzy patch kind of off the legs of Pegasus, which are the constellation Andromeda right here. And you can see this with your naked eye, unaided. No binoculars, glasses if you need glasses like me. And that's the farthest object you can see with a human eye anywhere on the planet. It's about 2.5 million light years away. Now during Hubble's time, about 100 years ago, a little less than that, but before that, 100 years ago, scientists all thought that the universe was essentially contained within the Milky Way. The Milky Way was the universe and everything belonged to the Milky Way, including what we knew of as the star nebula Andromeda, or M31 is its technical name. And so Hubble was actually studying these clouds of stars, that's what nebula means, thinking they were kind of groupings of stars on the sort of outskirts of the Milky Way galaxy, and that if he could figure out their distances, he could say how big the Milky Way was and say something about the size of our universe. And so this is an actual photographic plate from Mount Wilson almost 100 years ago, 1923, using a telescope the same size as the Hubble Space Telescope. And you can see he's written on it, and right here he's marked a little tick mark, and there's a little tiny dot there, and he wrote VAR with an exclamation point. And that's because he was excited because he realized he saw one of those pulsating stars, a variable star is what we call them. And he knew that was a jackpot for figuring out how far away that object was. And it turned out, at least according to his calculations, it was about 500 times further away than anybody thought. That means, just like that, the size of the universe became vastly much larger, 500 times 500 times 500 at least. And he immediately realized that this object he was looking at was not a star cluster, but another island galaxy of billions of stars, which we now see in a modern CCD digital camera image. His second great discovery is once he realized that these were important objects outside of the Milky Way, he continued to study them at Mount Wilson. This is a pretty cool picture. It shows Hubble's the tall guy in the back here behind Einstein. Einstein had visited there probably in the 1930s. And he still uses the 100-inch telescope to continue his work to study galaxies in more detail. And he did a really pretty basic experiment. He's like, well, I know these things are important, so I'm going to study a couple dozen of them, and I'm going to measure a couple other key properties about them. I'm going to measure how far away are they. So Andromeda is the closest one, so I'm going to find some other ones a little bit farther away, and then I'm going to find some way to measure how these things are moving. And he found this really interesting relationship. That's from his original paper in 1929. You can see if a galaxy is further away, it's moving faster. And actually, in all cases, every galaxy is moving away from us. Farther away, faster. Even farther, even faster. And that right there is expansion. If you make a raisin cake loaf and put raisins in the oven and bake it, and do a little experiment where you measure all the distances of the raisins, and then after an hour you measure them again, you'll get that same figure right there. You get expansion. That's what expansion is. And he realized this means the universe is expanding, which is our a clear or modern understanding of the universe. Now, what made these discoveries possible? I said he's given credit for it. Just like today, it took teamwork. So first of all, he relied on other people, and there's a couple people that weren't really given credit back then. They are now. One in particular is Henrietta over here on the left, and Vesto here on the right. She was a person who was paid at the Harvard College Observatory to actually do calculations over and over and over again and study detail. It was a pretty I don't know, tedious job, but she was university educated and she worked hard at her job, but she didn't simply make calculations. She was basically paid to be a calculator because we didn't have calculators. We had slide rules, so you need to have somebody do thousands of calculations or study thousands of properties of different stars. But what was so great about Henrietta is that she actually had the physical insight to realize that there was this relationship between stars that get brighter and fainter on a regular period. They're called Cepheid variables. She figured out the physics of why that's true and why that period of brightening, dimming has to do with how truly bright the object is, and lets us use those objects as a yardstick. We call them a standard candle for measuring how far away really distant objects are. So he couldn't have done that experiment without her, and he actually knew about her work because he wrote variable on the image. So he was looking for stuff based on her work. Second, to be able to measure distances, you have to be able to take the very faint light from a galaxy, spread it into a rainbow, look for these specific features, and from that you can, sorry, not distances, speed, you can get speed. And so Vesto here invented the first faint object spectrograph, which is this funny looking machine here that you can attach to the back of the telescope and get spectra from galaxies. So Hubble could not have measured his expansion of the universe, the velocity part of that plot. He couldn't have measured it without this instrument that Vesto had put together. Besides teamwork, we needed funding for the biggest and best telescope. The Mount Wilson telescope was biggest in the world at that time. About 100 years ago is when it was started. And it was the biggest telescope for the next 30 or 35 years. On the left, you see Andrew Carnegie, very rich person back then, who actually donated the money to build the Mount Wilson telescope. U.S. astronomy 100 years ago was done basically by a few people at a few elite institutions, funded by a few millionaires. They weren't billionaires yet. And that was it. So it was a very specialized group, an elite crowd, and we had to depend on a few rich people to actually cough up money to build this awesome technology. We also needed really daring engineering, so you can see the mount for the Mount Wilson telescope. This is the part of the telescope mounts onto and turns. You can see the guys up in the upper left. This is huge. This is the kind of engineering that they would use in building big ocean liners. So the other guy in this picture with Carnegie was the guy who put together the Mount Wilson Observatory. His name's George Ellery Hale. Him and Hubble got together after the successes of the Mount Wilson telescope, after the successes of Hubble's discoveries about the expansion of the universe and the size of the universe, and the fact that there's galaxies out there, they're not just star clouds. And they were very competitive guys. They knew that if we kept on building the best instruments and the best telescopes, we could be number one. Physics, science, astronomy was dominated into the 19th century and the beginning of the 20th century by the Europeans, and they really wanted to be number one. And so they kept on lobbying and pushing for more money to build an even bigger telescope. And they finally got money from Rockefeller to build the great 200-inch telescope in California, the Palomar. Construction started in 1937. About 11 years later, it was finished. And I'm taking down this memory lane for a reason. This is a really interesting moment in U.S. history as far as science goes. This moment marks a change from when we went to basically almost all science was done private funding to a time when we changed to a public funding, a public investment in science. Now, part of this was driven by this guy right here. He was the science advisor after World War II, and based on lessons from World War II, he realized that investing a little bit of the U.S. Budget into science could have big impacts on our health, in our national defense, and in boosting our economy. And so he lobbied, and he basically won through. And so in 1950, Congress created the National Science Foundation, and 8 years later, of course, because at least partly, or maybe completely, because of Sputnik, we had NASA founded. And I'm making this point, Vannevar Bush, he made the argument about economy and national defense. Another thing happened when we started investing money publicly in science. Again, we went from a few people at elite institutions funded by private money to now everybody at state universities could participate in the endeavor of science. And that sort of hope drove economic prosperity during the 1950s, partly, a lot of quality of life improvements, and it also was driven and drove the need for a stronger defense. We were worried when the Russians put Sputnik up above Earth that what if they could actually take bombs up there and drop them on our heads? And so I think a combination of hope and fear at that time after World War II really gave a lot of political will to actually invest a lot in science, a lot more than we do now. And I'm setting this up to show you what benefits we got out of that investment. So a key thing I want you to take away from this talk, besides that Hubble is really awesome, is that how much do we actually spend on science and what do we get for that? So starting with this investment in 1950, it basically ushered in this era of new national teamwork that made the US dominate science and especially astronomy in the world, at least until the 1990s. And I'm going to show this for a minute graphically like this. So I'll actually use a couple fun slides like this. So first of all, we dominated the exploration of the solar system, the inner solar system, the outer solar system, the 8 major planets shown here, all to the right scale as far as their size, but they're much farther apart. And so I'm going to show you in terms of flybys, landings, and orbits, chronologically the first at each planet. And you can see, except for a very few cases, the US completely dominated the exploration of the inner and the outer solar system in terms of landings, flybys, and orbits. We also were first in a lot of missions to comets and asteroids, including sample return missions. Of course, we were the first and only to land on the moon, and more recently, we're the first and only to go by and take really nice detailed images of the more minor, what we now call dwarf planets. So in the inner solar system, the biggest dwarf planet is Ceres here. It's the biggest and only really round or second round object in the asteroid belt. And then, of course, Pluto that we went by a couple years ago. Also, for astronomy, and this is really cool. Okay, so this graphic right here shows the surface of the Earth, and this diagram across horizontally represents our atmosphere graphically. And it's showing places in the electromagnetic spectrum. So some of you may know that besides the light we see with our eyes, there's a whole range of light that we cannot see. And being able to see that light, detect it and study it, gives us completely new information about the universe, new parts of the cosmic message from stars and galaxies in the distant universe. But the problem is, most of it can't reach the ground. It hits the top of the atmosphere and it gets stopped. Only visible light, a little bit of radio waves hit the ground fine, and a couple spots of the infrared, if you're kind of up in the mountains like right here, hit the ground, but all the rest is blocked. And so again, with our investments, we launched the first telescopes into space that could observe this hidden window and get all new views of the universe. And then this led to what is called the 4 great observatories, space-based observatories, including and starting with Hubble. So all this awesome science, and we were number 1 for 40 or 50 years, that's great, but what did it cost, and was it actually really worth it? And even in the 1960s, during the Apollo mission, when we were spending a lot more, there was a debate, a political debate about this. There were politicians that argued that we're in the middle of a war, the Vietnam War, we have other crises here on Earth, we shouldn't be spending money on going to the moon, doing any kind of this science space stuff. We have to be serious. And then there were people like Dr. Nancy Grace Roman here, that she realized in this, that's actually a fair argument. What are we spending and is it worth it? And she realized we actually really need to explain to the public, what are we getting, what are you all getting for your tax dollars? Basically, what are the costs of this research and what are the benefits of it? And she had this great quote. She was actually one of the early scientists to work on the Hubble Space Telescope, like the design phase back in the 1960s, and she said that for a single night at the movies for your family, you can get 15 years of exciting discoveries with the new space telescope. But the question is, who is right and how much actually was the cost, and how much do we actually spend now? And so I'm going to do something a little unusual. I'm going to show you a slide that I would show my intro astronomy class, and I'll ask you to actually vote. It's actually darker in here than I thought. So I'm giving you a hint. 25 years, the first 25 years of Hubble is about $10 billion. And I'm asking you, if for every dollar you pay in your taxes that you give to Uncle Sam, how much of that dollar do you think goes to all science? Not NASA, not Hubble, but every single national institutes of health, the weather, Department of Energy. Any ideas? Like, you got 5 choices up there. Big? A. So E or A?
B.
I hear, okay, how many people vote for B, 2 cents? Did you say A?
I said A.
How many people vote for A, 1 cent? Okay, how many people vote above 2 pennies? Oh, optimists. All right, so this is a good fact to keep in your pocket, to remember. All non-military research and development, innovation, science, by the US government's 2 pennies. 2 pennies of every one of your tax dollars. It's basically a penny for National Institutes of Health to study disease, cures for cancer, cures for disease. And the other penny goes for NASA and everything else. And you can see how it's changed. So the big humps are back at the beginning of the Apollo mission around 1962. And now we sort of flattened out to 2 pennies for quite a long time. And to put this into human perspectives, if you're an average taxpayer, that works out to be about that much a year. 40 bucks.
I spend that a night.
A night, drink that. You drink six, that's pretty good. Maybe a week, but. So like 40 bucks for an average taxpayer. And to go back to Nancy Roman's idea, it's actually more than she said. It's not a night at the movies for 15 years of science with Hubble, but maybe a night at the movies for 3 or 4 years. This is basically a night at the movies for every single man, woman, and child in the United States, covers all of NASA. Hubble's just a small part of NASA, actually. So it's about a night at the movies, just the ticket, 10 bucks will get you to the movies or have you have science projects from NASA for the whole year. And I actually want to borrow a page after Neil deGrasse Tyson, one of my heroes for promoting government investment in science and science in general. Neil deGrasse Tyson, he put this campaign a couple years ago out called A Penny for NASA, basically doubling the NASA budget, because the NASA budget right now is about half a penny. During Apollo, it was 12 times. 6 pennies just went to NASA out of every single tax dollar. But Americans loved it. Americans felt like we were all in this great adventure and new direction together. So he argued, let's double. And I actually say, let's not just double NASA, let's double the whole thing. Let's go from 2 pennies to 4 pennies. If we go for 4 pennies, well, just a penny for NASA, we will get all the kind of things that NASA scientists and engineers have been dreaming of, like putting people on Mars, building moon bases, maybe telescopes on the moon, going to the outer solar system and exploring these icy moons that might have life under the crust in the liquid oceans that we know are there. But some people say, that's all kind of dreaming and everything, but I think that Americans actually dream a lot about space exploration. And this is another thing I want you to think about. So Hubble's been around for 27 years. The total budget, building it over a couple decades, paying all those hundreds of people to do all the engineering, the hundreds of scientists that are using it at the institute that runs it right now on the University of Johns Hopkins University campus, launching it, maintaining it, building new instruments, launching those and putting them, all that is about $11 or $12 billion. And over that same 27 years, the top 18 grossing movies have more than paid for half of the Hubble price tag. Americans have spent $6 billion going to those 18 movies because we dream of going to space. That's pretty up to date. I think there's a new one I need to change out. All right, that's all great. Is it really worth it? One lecture slide. The evidence shows historically that since 1950, when we invested in science, the payoff has been gigantic. So economists estimate something between $10 to $20 return on every dollar spent. It takes a long time, it's long term, so no corporation is going to invest in something that has a 5, 10, 20 year payoff. And you can't pick one great scientist out of all the hundreds of scientists and count and bank on that they're going to come up with some cool gadget trying to study distant galaxies that then is going to turn into new industry that we can make these gadgets and mass produce them and sell them and have jobs here. But that's what happens when you invest a small amount widely all over the country. Also, that investment doesn't just go to the scientists, it actually goes to the communities around the institutes and the universities and actually regionally for all the people that support this endeavor. So it really is an investment in the community. And so from investing in our country, which is something I believe strongly in, it makes the most sense. And we're really talking a small amount of money, in my opinion. So again, I would argue let's double down. Not only do we get more economy boost, but we also inspire our next generation of scientists and engineers. They love building. I mean, it's a lot. When we did Apollo, people were inspired by the idea of trying to do this thing that nobody had ever done before. And that is actually a really positive place to be, I think, as a country. All right, I'm almost done. So, I think we're at a crossroads as far as the history, not the history, as far as the future of science and the future of astronomy. We've been on a pretty flat, kind of a little bit declining 2 pennies over the last couple decades. And so we could keep on that trajectory at this crossroads, or we could think bold and go for that double the budget, go from 2 pennies to 4 pennies. And I really do think in terms of what do we want to spend our money on, and do we want to invest in the future or worry about short-term things, it is kind of a question of hope versus fear. And it's a very timely question given that there are proposals to cut the little tiny 2 pennies down by 20%. It really is kind of fighting over scraps of the budget in the end. And a lot of people say, yeah, that's silly. You know, there's no way we're ever going to double the budget, even though at one time it was like 4 times, 5 times greater 40 years ago. This is just politically not possible. And that might be true, but I want to put it in perspective. So in 2009, we had the big crisis and the government bailed out the banks. And in one fell swoop, our politicians agreed to spend $750 billion in 1 year, less than a year. And that amount of money is basically NASA's entire history. Almost 60 years of everything that NASA's done, we did that at one. So we can make this decision when we feel like we have to or when we feel like we want to. And one last little point, there's people from all different political parts of the spectrum that make arguments. Conservative George Will made this recent argument I like a lot. He was talking about, he was thinking about and reflecting about the next telescope, the James Webb Space Telescope to follow up Hubble. And he was thinking about back during the Apollo time, yeah, we were motivated by the Cold War, but we produced all this awesome stuff like rockets and satellites and prestige. And he's like, you know, the Webb is not going to make us have a more strong defense, but it's going to make our nation all the more worth defending. And that's a great quote. So I would argue that if we double the science budget for all of science, it'll be great for cancer research, for knowing about hurricanes and tornadoes, for coming with new energy technology. For astronomy, we'll get everything we've been dreaming of. The new telescopes that will discover the first stars and galaxies, look for alien life. We have asteroids that impact the Earth sometimes and cause big problems. We could definitely do with spending more money looking at that. And again, inspire new generations of dreamers and thinkers and builders. And before I end and take questions, I just want to remind everybody that there's a total solar eclipse coming to your neighborhood very soon. Whatever you do, make sure you're where it's total. Not if you hear, oh, Lawrence is going to be 98%, that's not good. You want to go to where it actually the lights go out and it's a lifetime. I haven't even seen it, and I know that it's going to be a life-altering experience. So I would be remiss for not showing that. All right, and I'll roll credits and take questions.